Welcome to the Problemos channel season 2 episode 7, the episode which I titled 2 eggs versus 1 building, because in this episode we will discuss the solution of the wonderful problem that is our first computer science challenge S2CS1. And as a friendly reminder, if you're joining our channel mid-season, it is a good idea to find on the homepage of this channel the episode titled the Problemo channel how to, and watch that episode in its entirety, because in this episode we explain in excruciating detail why we do the things on the channel that we do, and this will align you with the overall program and make things easy to understand and follow the format of the presentation of the information of this channel. Meanwhile, we come back to the problem S2CS1. And as a reminder, in this problem, we're given 2 eggs, 100-story building, and we're told that if any of these eggs is thrown out of this building from any of the specific floors, then such an egg may break or may not break. And the intellectual challenge in this problem is to find the smallest number of egg drops and the corresponding testing scheme or the corresponding algorithm, which will determine with absolute certainty the lowest floor, the drop from which these eggs will not survive, because the idea in a somewhat humorous way is to presumably rate these eggs for break resistance, which means that, for example, if we found that the lowest floor, the drop from which these eggs do not survive is, for example, 7, then these eggs will be rated as 7 tough. Now, what does the break resistance of an egg mean? The break resistance of any of these 2 eggs means the following. Let's say we dropped any one of these eggs from the floor number K. We threw this egg out from the floor number K, it fell, and we see that this egg did break. What does that mean? That means that if these eggs, for example, the second egg is thrown from any higher floor or from the floor K plus 1, K plus 2, K plus 3, and so on, these egg will definitely break. Conversely, if we drop an egg from the floor number K and the egg does not break, then that means that if this egg or the other egg are dropped from any lower floor, from the floor K minus 1, K minus 2, K minus 3, and so on, then these eggs definitely will not break. And we want in this challenge to find the lowest floor, the drop from which these eggs will not survive. And for the abbreviation purposes, let us agree right away that with, for example, let me write it down here, LBF, with the letters LBF, I will designate precisely lowest, L for lowest, bad, B for bad, floor, LBF, lowest bad floor, and we will agree to define a bad floor as a floor, a drop from which the egg did not survive. Now, this problem is by now fairly well known in the corresponding circles. It's discussed on various problem-solving forums. As far as I'm aware, it was first published in 1992 in the book by Konhauser titled "Where Did the Bicycle Go?" That puzzle also appears in the book titled "Algorithmic Puzzles" by Anany Levitin. And again, don't worry about the names of the authors and titles of the book. I'll have them in the description of this video. There are various ways in which these problems are solved. And the reason why I wanted to bring this problem to your attention is because I think that in this particular case, it is very advantageous to see how the reverse order problem solving approach can be applied to the solution of this problem. As a friendly reminder, according to the reverse order problem solving approach, when we try to find a solution of a given problem in mathematics, theoretical physics, or computer science by using that approach, we temporarily suspend our effort to generate the traditional and sought after forward flow of causality. We switch things around and we take what's sought after as given, as input, as our initial point, and we try to string together a bunch of if P then Q implications and arrive at some material that is actually given in the problem. And the idea here that heuristically, again, there is no algorithmic guidance in this problem solving approaches that we study, but heuristically, we may gain enough of tactically useful information on the reverse order journey that will allow us to construct the sought after forward flow of causality solution. Now, when we attack the problem S2CS1 in real time, then again, it's advantageous to try to solve a similar but somewhat simpler problem. That is, can we determine with absolute certainty the lowest bed floor in the building with just one egg, and what is the corresponding testing schema? What is the corresponding algorithm? Well, in this case, it doesn't take much intellectual voltage or much intellectual challenge, but to see fairly quickly that there is only one algorithm, there is only one testing scheme that allows us to determine the lowest bed floor in the building when we have only one egg, and to do that with absolute certainty. And that scheme amounts to dropping the egg from the first floor and observing the result. If the egg breaks after it's thrown from the first floor, then the floor number one is the LBF, the algorithm terminates, and if the egg number one survived the drop from the first floor, we step up to the second floor only without missing any floors and repeat the experiment. We drop the egg from the second floor. If the egg breaks, then we declare that the LBF in this building is 2 and the algorithm terminates. And if the egg does survive the drop from the second floor, then we step up to the third floor and repeat the experiment, and so on. In other words, with one egg, with absolute certainty, the lowest bed floor in the building can be detected if the eggs are thrown consecutively from the floors 1, 2, 3, 4, 5, 6, 7, and so on, without any gaps and obviously without any overlaps. Now that we have the one egg testing algorithm on the books, we may step up and try to attack this problem when we're given 2 eggs. As a fair warning, it is a good idea to watch this episode with a bunch of paper and pen available, because I'll be doing a lot of writing and a lot of erasing. I have the limited resources, so everything that I write down will later become as explained earlier, so it pays to write down these notes as we go along. Very well. According to the reverse order problem solving approach, we begin the process of searching for a solution of this problem from its final state. And what is the final state in this problem? The final state in this problem is where we're standing on the 100th floor, and we have both eggs intact in our hand, and we execute the last throw, the throw number n, which for now, right now, is a mystery. We don't know what this floor is, but what this drop is, but with the drop number n, we throw the egg number 1 from the 100th floor. Let us write it down over here from the floor 100. We execute the drop number n. Now, this notation may look a little funny, but let us agree right away that in the scheme that we will be developing over here, the number represents the floor number from which the drop number subscript is executed. Consequently, this bunch of symbols can be interpreted as follows. From the floor number 100, we execute the drop number n. And for a more expedient symbolic manipulation, let us agree that D will designate the drop, the subscript will designate the drop number, egg number X, and floor number Y, like so. And again, this string of symbols can be deciphered quite straightforwardly. We will understand that this means the following: the drop number n of the egg number x from the floor number y. Consequently, when we're standing on the floor number 100 and we execute the drop number n, the drop number n of the egg number 1 standing on the floor 100, then what are the two possible outcomes of this experiment? Well, if this drop is, let's say, good, we'll designate it with the letter G, and the drop is good if the egg, when thrown from this floor, did not break or survived the fall. Then what does this outcome mean? This outcome means that in this case, we'll say that if the drop number n of the egg number 1 from the floor 100 is good, meaning that the first egg when thrown from the 100 floor did not break, that means that the LBF, lowest bed floor, in this building is not existent, and tentatively, using the artistic license, we'll designate this with the symbol for the empty set. There is no lowest bed floor in this building, and these eggs are too tough for this building. We'll probably need a higher building to break these eggs. Else, if the drop number n of the egg number 1 from the floor 100 is bad, the egg did break. Then what does that mean? That means precisely that the LBF, or the lowest bed floor in this building, is precisely 100, because according to the mystery scheme that we are yet to uncover, we tested all the previous floors, and the drop from all of these floors from the first egg did not break it, and it so happened that the drop from the 100 floor of the drop number n did break the egg, and the lowest bed floor is 100. Very well. It's a good idea to write this down because I'm about to erase it. And now, because we're solving this problem in reverse order, we now ask the following honing question: from which floor did we ascend to the floor number 100? Excellent. From our previous episodes, recall that when we explained how the reverse order problem solving approach works, that, for example, when someone, let's say the mathematical or the computer science oracle, was performing the test and we managed to take the movie of that oracle executing that scheme, we now wonder from which floor did we or the oracle ascended to the floor number 100. Well, let's say that that floor is f sub x, for example. This floor is f sub x. The floor is f sub x. We'll designate the motion upwards with the green arrow, like so. And what does that mean? Well, we will note again that if the drop number n minus 1, now we have to be careful because we are solving this problem in reverse order. That means that instead of the drop number n, we are now executing the drop n minus 1, and we're still doing it with the egg number 1 with the floor from the floor number f of x. And if the result of this drop was good, meaning that when the first egg was dropped from the floor f sub x and it did not break, then that outcome of this test forced us to do what? What precisely? It forced us to climb up to the floor number 100, execute the drop number n, and in this case, as I gave you guys the warning before, as explained earlier in our previous analysis, if then, we execute the drop number n and we terminate our test regardless of the outcome of the drop number n from the 100th floor. Whether the egg breaks or doesn't break, the situation is covered. And now let us say if the drop number n minus 1 of the egg number 1 from the floor f sub x from the mystery floor was bad, b for bad. What does it mean? It means that when we dropped the egg number 1 from this floor, we witnessed the fact that the egg shattered into pieces, broke, and again, it should be evident that when the egg breaks as a result of the fall, then it cannot be reused anymore, it must be tossed. And if the egg did not break, then it can be reused again and again. In this case, if the drop number n minus 1 of the first egg from the mystery floor f sub x is bad and the egg 1 broke, what does that mean? Well, that means that the egg 1 is no more. We don't have it. We have only egg number 2 left. And how many drops do we have in our budget? Well, we have only the nth drop, in our budget, which corresponds to precisely 1 drop. Precisely 1 drop. And this is where the reverse order problem solving approach meets the tactical advantage. If we have 1 drop and 1 egg, then how many floors can be tested with absolute certainty in this case? Well, that is why we solve the problem, the simpler, similar problem ahead of time. And according to our 1 egg testing strategy, that means that in this case, with 1 egg and 1 drop, we can test precisely 1 floor. And in this case, it means what? If the egg number 1 did break after the drop number n minus 1 from the floor f sub x, does it mean that the floor f sub x is the lowest one? No, it doesn't mean that, because the lower floor can be bad as well. And that means that for the nth drop of the egg number 2, we will descend to the floor, which one? X minus 1. We will execute the drop from there. And if this floor is, if the drop number n minus 1 of the egg 1 from the floor f sub x is bad, then we execute the drop number n of the egg number 2 from the floor fx minus 1. And if this drop is good, then what does that mean? Well, in that case, yes, it means that the LBF in this building for this egg will be fx, and else if, for example, we'll write it down, we'll spell it out, if drop number n of the egg number 2 from the floor fx minus 1 was bad, that means what? That means that the LBF in this case is what? It's precisely the floor fx minus 1. But because no floor in our testing algorithm can be left not tested, it should be now evident that the only choice for the floor f sub x is what? The only choice for the floor f sub x is the floor 100 minus 1 or the floor number 99, which is what we write on our scheme over here, 99, drop number n minus 1. And if the drop from the floor number 99 is bad, then we do what? Then we descend to the floor fx minus 1, and in this case the floor fx minus 1 will be what? 99 minus 1 equals 98. So in this case we descend, we'll show the descent with the red chalk. We descend to the floor number 98, and we execute the drop number n. So far our testing scheme unfolds as follows. On the floor number 99, we execute the drop number n minus 1, and if the first egg breaks, we descend to the floor 98 and execute the drop from there. If the egg survives the drop from the floor 98, then the lowest bed floor is the floor 99. And if the egg does not survive the drop from the floor 98, then the lowest bed floor in the building is 98. However, if the first egg does survive the drop from the floor number 99, we step up to the floor number 100 and repeat the experiment as was explained earlier. Again, it makes sense for you guys to write this down because I'm about to erase it, but as another thought experiment, let's say, for example, we decided that the floor fx is not 98, but it's, for example, 90 is not 99, but the fx is temporarily is 98. Again, we execute the drop number n-1 on that floor, and if the drop of the first egg from that floor results in the first egg not breaking, then we have a gap, the floor number 98, the floor number 100, which we know we tested in our reverse flow of reasoning. But what about the floor 99? Remember that the drop number that we executed on this floor by temporary assumption is n-1. That means that in our budget we have only one drop to execute, the drop number n. And with one egg and one drop, how many floors can be tested? Well, according to our one egg testing scheme, only one floor can be tested with one egg and one drop. Consequently, if we execute the drop from the floor 99, the floor 100 remains uncovered. And if we not tested, and if we execute the test from the floor number 100, then the floor 99 will remain not tested. That is not acceptable. That is why the only choice over here for the floor f sub x is 99, and our testing scheme so far looks as follows. I will write down the testing scheme, the floors over here, so that we keep track of it. We throw the egg from the floor 100, and then before that floor 99, and we keep solving this problem in reverse order. And now we ask the next honing question: from which floor we, or the computer science or the mathematical oracle whom we recorded during their forward motion, ascended to the floor number 99? Very well. Recall that right now we're watching the movie of the mathematical oracle or the computer science oracle executing their testing scheme in reverse order. And the question that we're trying to answer right now: from which floor did we, or the mathematical or the computer science oracle, ascended to the floor number 99? Again, let this floor be f sub y. If we do the same, keep doing the same analysis, if the drop number what? In this case, it will be the drop number n-1 was spent on the floor number 99. So right now it will be the drop number n-2. And this will be again done with the egg 1 from the floor f sub y. We do not know what this floor is. If this drop is good, which means that when we dropped the egg number 1 from the floor number f sub y on the attempt number n-2, and that egg did not break, then we climb up to the 99th floor. But if this drop was bad, we'll designate it with B, which means that when we drop the egg number 1 from the floor f sub y on our n-2nd attempt, and we witnessed the fact that this egg broke, then this egg no more. We don't have the egg number 1 anymore. We do have egg number 2. We have one egg at our disposal. And how many drops do we have at this point in our testing budget? Well, let us count. We already spent the drop n-2. This experiment is gone. on the books. So what is left in our budget? The drop number n-1 and the drop number n. So this altogether amounts to 2 drops. Exactly and precisely 2 drops. And here again, we go back to our 1 egg testing algorithm and we inquire with 1 egg and 2 drops how many floors can be tested with absolute certainty in order to determine the lowest bad floor in the building. And we know the answer. Precisely 2 floors can be tested with 1 egg and 2 drops, and we know how to do that. We descend to the lowest floor, or we descend to the floor, let's see, if drop number n-1 of the egg number 2 from the floor fy-2, if the drop number n-1, remember that we executed the drop n-2, so right now we're executing the drop number n-1 with the egg number 2 from the floor fy sub 2, and if that drop is good, then we execute what? We do the if drop number n of the egg number 2 from the floor f sub y-1, and we analyze the result. If that drop is good, then the lowest bad floor was the floor f sub y, and if this drop is bad, then consequently the lowest bad floor in the building is fy-1, because again, according to the mystery scheme that we're trying to unwind, if this is bad, then the lowest bad floor will be fy-1. Again, I will not be writing down all the possible scenarios in excruciating detail. You guys have pen and paper, please do so. Keep good records of this. But right now, because again, no single floor in the building can be left not tested, then what is the possible value for the floor f sub y? Well, it should be evident that the value for the floor f sub y should be what? 98 minus 1 is 97, and the floor fy-2 will be 97 minus 2, it will be 95, and the floor fy-1 should be 97 minus 1, or 96. And thus our testing scheme unfolds as follows. Make sure that you guys wrote this down. I'm about to erase it to make room for the our next step. Let me erase this too. Now, with the green arrow, we designate the motion up. The motion up. We came here from the floor number 97, where we executed the drop number n-2. And then if the drop number n-2 from the floor number 97 is good and the first egg did not break, we climb up to the floor number 99, and in how many? In 2 drops, the drop n-1 and the drop n. Either way, we test all the remaining floors in the building, and if the drop number n-2 from the floor 97 of the first egg resulted in this egg breaking, we do what? We descend to where? We descend to the floor number 95. Over there, on that floor, we execute which drop number? Correct, the drop number n-1. And if the egg survives that drop, we climb up, show it with the green arrow, to the floor number 96, where we execute the last drop, or the drop number n. Again, I recommend that you guys keep good records of what I have on the board, because I'm about to erase it, but we keep solving this problem in reverse order, and now we ask the next question. From which floor did we ascend to the floor number 97? Very well. We keep watching the movie of the computer science oracle, weaving their magic and executing the 2-egg 100-story building testing algorithm in reverse order. And we now inquire from which floor did we or the said oracles ascended to the floor number 97. Again, we will execute the similar analysis that we did in the previous segments. We will designate the motion upwards with the green arrow. We know that at this point we will execute the drop number n minus 3. And again, by doing the similar analysis and writing down, let's write this number down, 97 here. By writing down the various cases, if the drop number n minus 3 from the mystery floor f sub z, for example, was good, then we ascend to the floor number 97, and in precisely 3 drops, the drop number n minus 2, the drop number n minus 1, the drop n, no matter what the outcomes is, we test absolutely all the floors starting from 95 to 100, 95, 96, 97, 98, 99, 100. And if the drop number n minus 3 from the mystery floor f sub z is bad, in other words, we dropped the first egg from the mystery floor on the attempt n minus 3 and the egg did break, then what will we have? Again, the first egg will be gone, no more. We'll be left with the second egg, but this will be only one egg. And how many drops will we have in our budget? Well, we will have exactly n minus 2, n minus 1, n for the drop number. So we'll have precisely 3 drops in our budget to test the floors beneath the mystery floor f sub z. And how do we do that? Well, we already know through our previously solved simpler problem. According to the one egg strategy, the only number of floors that can be tested with absolute certainty with 3 drops and 1 egg is 3 floors. So we will correspondingly descend to the floor f sub z minus 3 and then ascend to the floor f sub z minus 2, f sub z minus 1. And because no floor in the building can be left not tested, it follows that the candidate for the floor f sub z will be 95 minus 1, or the floor number 94. And on that floor we will execute the drop number n minus 3. If the first egg does survive the drop from the floor number 94, we climb to the floor number 97 and execute our miniature algorithm, which covers all the floors as described above. And if the first egg does not survive, then we descend to where? We'll show the descent with the red chalk, with the red arrow. Then we descend to the floor 94 minus 3 is 91. We descend to the floor 91, and on the floor 91 we execute which drop number? Correctly execute the drop number n minus 2. If the second egg does survive that drop, we climb up to the floor number what? 92, and we execute which drop number from the floor 92? Correct, very well, the drop number n minus 1. And if the second egg does survive the drop from the floor 92, we climb up to the floor number what? To the floor number 93, and on that floor, or from that floor, we execute what? The drop number n. And depending on the outcome of the drop, we already understand how the algorithm will play out. This scheme over here should be evident because it plays out precisely according to the one egg testing algorithm that we developed before we started solving this problem. Again, in real time, when, for example, I was solving this problem, I was way more patient and stubborn. I wrote down a lot of these numbers, and again, I recommend that you guys do that as well. But again, we keep solving this problem in reverse order, and we ask the next honing question. From which floor did we, or our favorite oracles, ascended to the floor number 94? Again, we'll mark the ascent motion up with the green arrow. Here we executed the drop number n minus 4. N minus 4. Again, at this point, if the egg number 1 that was dropped from this mystery floor did not break, then we ascend to the floor 94 and we test all the floors in the building starting from the floor 91, 92, 93, all the way to the floor 100. But if the first egg does break and does not survive the fall from this mystery floor on the temp number n minus 4, then what do we have? We have still the egg number 2, which is only one egg, but how many drops do we have in our budget? Well, we have the drops number n minus 3, n minus 2, n minus 1, and n, and altogether that corresponds to 4 drops. And then what is the candidate for this mystery floor over here? Well, it should be, since no floor can be left not tested, it has to be tight with the floor 91. So the only choice here will be the floor number 90. The floor number 90. The floor number 90, from which we execute the drop number n minus 4. If that drop is good, we climb up to the floor 94. If that drop is bad, we descend to where? We descend to the floor number 90 minus 4, 86. And starting from the floor 86, we execute the drop n minus 3. If the egg survives that drop, we climb up to the floor number 87, from where we execute the drop number n minus 2, n minus 2, n minus 2. If the egg survives, the second egg survives that drop, we climb up one floor at a time to the floor 88 and execute the drop n minus 1. So far so good. All this unfolds. There should be no mystery here. All this miniature sub-algorithm unfolds according to the one egg testing algorithm. And if the egg number 2 survives the fall from the floor number 88, we climb up to the floor 89, and from the floor 89, we execute the drop number n, and the result of that test will terminate the algorithm and determine the fate of the lowest bed floor in this building. Again, in real time, we may patiently write more and more numbers in that fashion, but right now we step back, and as the German mathematician Carl Gauss used to say, from far away a solution to the problem may reveal itself. So when we look at this sort of directed graph, then what do we see? Well, what we see is the following. As we write down more and more numbers, and again, in real time with pen and paper, we'll have more numbers available to us, but eventually we will reach the following conclusion, and that is the whole idea of using the heuristics of the reverse order problem solving approach by trying to unwind the mystery algorithm in reverse order to see how it plays out in reverse order. Then we gain some competitive advantage and try to do understand how things work in the traditional forward flow of causality. So the idea or the pattern that we spot in this version of the directed graph is the following. The node-wise distance from the leftmost node in our graph on the same level or above to the terminal node is always one and the same or remains invariant. It's a constant. For example, what is the distance from the node named 90 to all the terminal nodes in this graph? Well, let's count. From the node named 90, we go on the same level. 1, 2, 3, 4. So that is the number 4. What is the distance from the node named 90 to all the terminal nodes above? to the node 93, for example? Well, we count 1, 2, 3, 4. 4 again. What is the distance from the node named 90 to the terminal node 96? Well, let's count. 1, 2, 3, 4. 4 again. What is the distance from the node named 90 to the terminal node 98? Well, it's again 1, 2, 3, 4. And finally, what is the distance from the node named 90 to the terminal node 100? That distance is 1, 2, 3, 4. And like I said before, in real time, when we have more and more rows that seemingly form an equilateral triangle available to us, that pattern will basically has no chance but to jump at us, at which point we will realize, aha, the distance between the floors from which we throw the first egg, egg number 1, 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 grows in arithmetic in arithmetic progression as follows. The distance from 100 to 99 is 1. From 99 to 97 is 2. From 97 to 94 is 3. From 94 to 90 is 4. And again, as we construct more and more nodes in this directed graph, very soon, actually, we will run into a situation when we cover all the floors. We'll have a fairly sizable equilateral triangle, and that pattern will hold, and we can now complete our testing scheme and write down the numbers. So after 97, there goes number 94. Then goes 94 minus 4 will be 90. 90 minus 5 will be 85. 85 minus 6 will be 79. 79 minus 7, 72. 72 minus 8 will be 64. 64 minus 9 will be what? 55. 55. 55 minus 10, 45. 45 minus 11, 34. 34 minus 12, 22. 22 minus 13 is 9. 9. And that is where our testing scheme terminates in reverse order, which means that in the forward flow of causality, this is where our scheme will begin. And that is so because from 9, we of course can subtract 14, but then we'll go underground. This is the terminal step. And now we begin to see what is going on. By coming up with this experimental testing scheme by reasoning in reverse order, we see that we partition the set of 100 floors into what we may call brackets. The first bracket will be from the floor number 1 to the floor number 9. The second bracket will go from the floor 10 to 22. The third bracket will go from the floor 23 to 34, and so on. And our testing algorithm becomes the following. From each of the floors written over here, we drop the egg number 1. If the egg number 1 does not break or survives the fall from each of these floors, then we step to the next floor in this bracket. But if the first egg, when thrown from any of these floors, does break, then we descend to one floor immediately above the last highest good floor. For example, let's say we drop the egg number 1 from the floors 9, 22, 34, 55, 64, 72, 79, and then on the floor number 79, the egg number 1 did break. Does that mean that the floor 79 is the lowest bed floor? Well, it may or may not, but there is no guarantee. So now, with the second egg, we descend to the floor number 73, and we test in succession the floors 73, 74, 75, 76, 77, 78, and so on, as we explained over here. Now, if we count the number of such tests in the worst case scenario, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It looks like 14 drops seems to be the smallest number of attempts, and the scheme, the algorithm that we described over here, that can be used to determine the lowest bed floor in the building with absolute certainty. Now, when we step back and look at our graph, which again in real time and on paper will be more data available, but how does the number of drops correspond to, how can we connect this number of drops to the height of the building measured in floors? Well, again, it's not difficult to see that what we have here is the way in which the attempts are connected to the number of floors. How? Well, this looks like triangular numbers. 1 floor plus 2 floors plus 3 floors plus 4 floors plus 5 floors and so on. Consequently, the mystery number n of drops, let's call it number x, the mystery number x will be connected to the height of the building as follows. The sum of the consecutive positive numbers, the first x consecutive positive numbers, must be greater than or equal to the height of the building in floors. In other words, the sum of k, where k goes from 1 to x, must be greater than or equal to the height of the building in floors, which in this case is 100 floors. We know that there is a alternative representation for that sum, the sum of the first x consecutive whole positive numbers. That sum is given by x times x plus 1 over 2. And with our constraint, that number must be greater than or equal to 100 floors. And at this point, it's quite straightforward to solve this inequality. Once we multiply it through by 2, we get what? X squared plus x minus 200 must be equal, greater than or equal to 0. If we temporarily treat it as an equation, a quadratic equation, then we will have for the roots of this equation -1 plus minus square root of 1 minus 4 times 200 will be 801 over 2. Approximately this will be -1 plus minus 28.3. We can do this by estimation, by bracketing above and below. For example, 30 squared is 900, so that's more. 25 squared is 625, that's less. So little by little we arrive at this number, and these numbers come out to minus 14.65 and plus 13.65. But because this inequality needs to be solved over the set of positive integers, the first smallest integer that, when plugged into that inequality, will make it true will be, of course, in the integers will be 14, and this is our number. Again, for those who may, for example, demand a little bit more graphical representation, graphical representation of this inequality will have a horns up parabola that goes something like this. This is y-axis, this is x-axis. So this root right here will be positive 13.65. This point right here will be negative 14.65. So the whole inequality will correspond to this region in the plane. And consequently, the first integer, the smallest integer that's still larger than 13.65, and make sure that the value, the corresponding value is greater than 0, will be 14. And at this point, we also now understand that if we plug in 14 directly into our formula, then what will we have? We'll have 14 times 15 over 2. That will be 7 times 15. That will be 105. So the tallest building that we can test with 2 eggs, apparently 105 stories tall. And that also, by the way, means, if we think about it, that the testing scheme that we presented over here is not unique. We can also execute. We still have room for 5 more testing schemes, or for 5 more ways to partition the 100 stories of the building into a scheme that will, with absolute certainty, reveal the fate of the lowest bed floor with 2 eggs and 100 stories. And that testing scheme will begin here with the floors number 10, 11, 12, 13, and 14. Again, please make sure that you take good notes of this material. I'm about to erase it, and because I do not want to bore you guys with watching me write down the scheme, here it's quite simple. For example, 9 plus 5 is 14 is the last floor. The last, that's our bracket size is 14. That's the last floor from which we can begin executing our egg and building testing algorithm. And consequently, for all these numbers over here, we simply add 5 and we get, for example, 27 plus 34 and 5 will be 39, and so on. Let me take a little break here and erase what we have so far and write down the entire scheme that will cover the test of all 105 stories. Very well. In order to spare you guys the pain of watching me writing all these numbers down, as a separate and formal exercise, I do recommend that you write down by hand explicitly the testing schemes, all the intermediate testing schemes, the ones that start with the floor 10, 11, 12, and 13. That is quite simple. You simply add 1, 2, or 3, or 4 to all the numbers over here as you raise the first floor for your testing scheme. And for the testing scheme for the building that is 105 floors tall with 2 eggs and 14 attempts, that testing scheme, that partitioning of the building is written over here, just to make sure, if you guys cannot see it, you have problems seeing these numbers, I'll sound it out. The first floor will be 14, 27, 39, 50, 60, 69, 77, 84, 90, 95, 99, 102, 104, and 105. This is all excellent, but as we note on this channel, mathematics is the foundation of theoretical physics and computer science, and computer science is not the same as computer programming. These are two different animals. In computer science, we want a proof. Ideally, we want a proof for various things. So how would you prove, for example, that 14, let's write this number down some here. Well, this is the guy right here. That 14 is the smallest number with which, the smallest number of drops with which a 105-story building can be tested with 2 eggs with absolute certainty and determine the fate of the lowest bed floor in the building. Well, here is my take. If you have a better, more crisp, more elegant, more enlightening proof, then by all means, be my guest. Don't be shy. Write down to me, maybe on Quora in direct messaging or some such, and maybe leave the comments in the comment section to this video. But I'll present you my version of the proof. Let's say the main idea over here is to observe the following. If we throw an egg from any floor of the building, then how many outcomes of this drop there are? there are only two outcomes. This egg either breaks or does not break. So when the egg breaks, for example, and shatters into pieces, then to that event we associate the binary digit 1, and if the egg does not break and remains intact, then to that outcome we associate the binary digit of 0. And now the key tactical maneuver over here is to take the number of drops, which in this case will be 14, but writing 14 bits on the board in real time, it will be too boring for you. So let's compress the number of drops. Let's say we'll work with 4 drops just for demonstration purposes, but that doesn't really matter much. So let's say we have D as the number of drops. Then we represent this number of drops. We associate D binary digits, D bits, and we number these bits left to right, starting from 1. So the rightmost bit position over here in this representation of the number of drops will be 1. The next ordinal number of the next bit position will be 2. The next one will be 3, and the next one will be 4. Now, when we execute a testing algorithm, whatever it is, it doesn't really matter. It doesn't have to be this specific algorithm that we presented here. We reason very generally and very, very theoretically. No matter what the testing algorithm you present or can be constructed in this case, there are only limited number of outcomes in this scenario with respect to eggs breaking or not. First of all, it may so happen that 0 eggs break, and then if we execute, for example, as a temporary stand-in 4 drops, we see on the drop number 4 no break, drop number 2 no break, drop number 3 no break, drop number 4 no breaks. It means that in this building the lowest bed floor does not exist. It's a possible outcome, and that outcome is captured with 4 zeros recorded as follows. But it may also happen that precisely 1 egg breaks. And when 1 egg breaks, what does that mean? How do we interpret this combinatorially? Combinatorially, we interpret it as follows. In order to cover all the possible outcomes of 1 egg breaking during any algorithm whatsoever, we need to distribute one indistinguishable item, the binary digit 1, over D, or 4 in this case, distinct buckets, where each bucket is basically a numbered position of the bit in the bit string. And for example, this can be done how? Well, it can be recorded as 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0, like so. So this number of outcomes of any algorithm, testing algorithm whatsoever, when precisely 1 egg breaks, can be accounted for in how many ways? Well, it will be in this case, for example, 4 choose 1, the binomial coefficient 4 choose 1, and the remaining outcome, because we have 2 eggs, no matter what the testing algorithm anyone comes up with, in this testing algorithm it can so happen that 2 eggs break, and in this case, just using 4 as a stand-in for D bits, we can record this outcomes which way? 0, 0, for example, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, then 0, 1, 1, 0, 1, 0, 1, 0, and 1, 1, 0, 0. This number, 1, 2, 3, 4, 5, 6, the total number can be accounted for combinatorially how? The total number of these outcomes, no matter what the algorithm is, can be accounted combinatorially by counting the number of ways to distribute precisely two indistinguishable items, two binary digits, one, across four, or D in general, distinct buckets. Bucket name number 1, 2, 3, 4, and so on till D. So this can be done in this case as 4 choose 2, or the binomial coefficient 4 choose 2 ways. We obviously understand that in general this will be done in D choose 1 ways, or D choose 2 ways for the number of drops. And here we obviously, this is a degenerate case, in which case we need to distribute 0 indistinguishable items across 4 distinct buckets. We capture this with 4 choose 0, or D choose 0 ways. And here is the delicate maneuver, because one given building, can have either no lowest bed floor, which corresponds to this case right here, when the outcome of the algorithm whatsoever was recorded as a bunch of zeros, or this particular building will have precisely one and only one lowest bed floor. In other words, it can never happen that one building can have 2, 3, or 4, or more than one lowest bed floor, and that outcome will be captured with one of these binary strings. Consequently, the sum, let's designate it the sum, in this case 2 eggs, and the number of drops D will be D choose K, where K varies from 0 to 2 in this case, will represent what? How do we connect that sum to the height of the building? Well, that connection can be done using the pigeonhole principle. If we associate a floor or floors with pigeons and the possible outcomes of this specific test with pigeonholes. And what does the outcome mean? The outcome, any outcome of any testing algorithm whatsoever, means that, for example, this result corresponds to lowest bed floor being X. This outcome means the lowest bed floor is Y, and so on. So if we assume that number of floors in the building will be greater than this sum, then that means that at least one pigeonhole will have more than one pigeon, is it? And in our case, we interpret it as follows: at least one outcome, or at least one lowest bed floor number, will share or contain multiple floors, more than one floor. But that is absurd. That can never happen. Consequently, that means that our assumption here must be changed to logically opposite. So that sum must be greater than the height, greater than or equal to than the height of the building expressed in floors. And again, because the outcome when no eggs broke means that there is no lowest bed floor in the building, means that we can throw it out and actually begin rolling our sum, starting with the coefficient, with the index, with the variable 1. And it should be evident also now that when we use 2 eggs for our proof, then this number of eggs can be replaced with any generic whole positive number whatsoever. So our master formula, so to speak, that we deduced together will depend on the number of eggs E. We'll capture the number of eggs with E, and we'll sum, the upper bound of the sum will be E, and this is the formula that we will use for demonstration purposes. So now let us give or take this formula for a test drive. If we have, again, This formula, by the way, can be used in both directions. For example, if we know the number of eggs and we know the number of drops, then we can compute the tallest building that can be tested with that many eggs and that many drops. And conversely, for example, if we know the number of eggs and we know the height of the building that we need to test, we can solve this inequality for D. We can designate it X if we want and recover the number of drops with which the building can be tested. In our case, let us do just that. If we have two eggs, so E equals to 2 in this case, then what will the sum look like? The sum will contain precisely two summands. It will be X choose 1 plus X choose 2, and that sum must be greater than or equal to 100, because this is precisely the height of the building that we're given in this problem. Well, that much we can handle. This is nothing more than our favorite middle school combinatorial analysis. The first binomial coefficient X choose 1 becomes X. The second one becomes what? Well, let's spell it out. It's X factorial over 2 factorial times X minus 2 factorial. So far so good. So the X minus 2 factorial in the denominator cancels out with the same factorial in the numerator. And what do we have left? We have X plus X minus 1 times X over 2, which still must be greater than 100. Well, here, let's multiply this inequality through by 2. What will we have? We'll have 2 times X plus X minus 1 times X greater than 200. That maneuver should be understood. This is probably even before middle school. This is nothing magic over here. Now we open up the parentheses, move 200 to the other side, and we get 2 times X plus X squared minus X minus 200 greater than 0. 2x positive, 1 copy of x negative cancel each other out, and what do we have? X squared plus x minus 200 greater than or equal to 0, and our formula magically and wonderfully reveals the same answer that we obtained previously when we claimed that the number of drops that needed for the testing correlates to the height of the building in the following ways. In the following way, the total sum of the first n or 14 whole positive numbers must sum to at least the height of the building. And we already know that over the set of positive integers, x must be equal 14. And this, by the way, combinatorial proof is a proof of a theoretical lowest bound, or the lowest number of tests that will guarantee with absolute certainty the detection or the fate of the lowest bed floor for the building that is 100 stories tall and with 2 eggs. And we now understand how to take this. For example, let's analyze this situation when we have 3 eggs. Before we jump into the analysis of the 3-egg case, I want to make sure that you guys understand and we're all on the same page about where did this formula come from. One more time, I just want to say these words, that the sum of the numbers, the total sum of the numbers of all these binary strings, each of which captures a particular outcome of the test of what's our algorithm, no eggs broke, precisely 1 egg broke, and precisely 2 eggs broke, should be at least the height of the building F. And we showed that by using the pigeonhole principle, by associating the floors with pigeons and the outcomes with pigeonholes. And now we can attack the case when we have 3 eggs. When E equals to 3, for example, what can we do in this case? Well, the binary capture the outcomes, they have certain patterns, and these patterns can be captured with the binomial coefficients, and that's how the binomial coefficients make it into the master formula shown above. These binomial coefficients will unfold into 3 when we have 3 eggs, and what will we have? We'll have x choose 1 plus x choose 2 plus x choose 3, which must be greater than 100. Again, this formula, this result should be evident how we obtained it from this formula, which we obtained again by summing the total number of the binary strings that capture the possible outcomes of any algorithm. Because number of eggs equals 3, we run this sum from 1 to 3, like so, and now we simply unzip this binomial coefficients, and we get x plus x minus 1 times x over 2 plus this one we will do on the fly, x factorial over 3 factorial times x minus 3 factorial cancel each other out, and what do we have? We have x minus 2 times x minus 1 times x over 3 factorial is 6. 6 is 2 times 3 greater than 100. Again, that should be no mystery whatsoever. We see that this is the common term between these two summands, so we have x plus x minus 1 times x over 2 taken out, 1 plus what do we have left? X minus 2, x minus 2 over 3 greater than 100. Again, that maneuver should be understood. The common term x minus 1 times x over 2 is taken out, x minus 2 over 3 is left over. Here we bring this under one denominator, 3 plus x minus 2 becomes what? Becomes x plus 1, so we have x plus x minus 1 times x plus 1 over 2 times 3 is 6 greater than 100. Again, that much should be understood. That is quite straightforward. We can do it in our mind. We do not need pen and paper. X minus 1 times x plus 1 is the difference of squares. X plus x squared minus 1 times x over 6 greater than 100. Again, we just combined x plus 1 and x minus 1 into the difference of squares. Now we multiply this inequality through by 6. We have 6x plus x cubed minus x greater than 600. Again, we multiply this through by 6. We get 6 times x here, x cubed minus x greater than 600. 6 positive copies of x and 1 negative copy of x cancel a little bit, and what do we have? We have x cubed plus 5x minus 600 greater than or equal to 0. This is our equation. This is known as a depressed cubic. I can probably deliver another 2-hour lecture about depressed cubics, but for now this is not the point of this episode. We know how to solve these equations very well. This comes out if we plot the roots of this equation in the complex plane. It turns out that there are 2 complex roots, which are conjugates, of course, and 1 real root, which is approximately 8.2368 approximately, which means that over the set of integers, x in this case comes out to be the number of drops, comes out to be precisely 9 drops. So in 9 drops with 3 eggs, we can test 100-story building with absolute certainty and uncover the fate of the lowest bed floor. Again, please make sure that you have all this information copied to your notes. This is not complicated, this is straightforward, nothing but, again, middle school arithmetic. And now the interesting question is the following. From which floor do we begin our 3-egg testing scenario in this case? Well, again, we reason the same way in which we reasoned before with the 2-egg case. Let's say we drop, this is our base floor, we drop the first egg from the floor f sub x. If the egg number 1 does not break, we climb up somewhere, but if the egg breaks, then what? That means that we will have 2 eggs, and how many? 9 minus 1, 8 drops left. So the question is, with 2 eggs and 8 drops, how many stories can we test, or what's the tallest building that we can test? Well, this is our wonderful formula. This is where our wonderful formula comes in. We have, for the height of the tallest building that we can test with 2 eggs and 8 drops, we have what? 8 choose 1 plus 8 choose 2. This must be what? 8 plus 7 times 8 over 2. That will be what? 8 plus 7 times 4. So 8 plus 28 comes out to 36. So now we see that with 2 eggs and 8 drops, we can test a 36-story building. Wonderful. So that means the floor immediately below f sub x is 36. And that means that the floor from which we begin our testing of the building with 3 eggs will be what? Will be precisely 37. So let's write down that number over here. We will begin testing our building with the floor number 37. Wonderful. Now, what is the next floor to which we climb if the first egg does not break when thrown from the floor number 37? Again, we already know how to solve this problem. In this case, we will have, if the egg thrown from that mystery floor breaks, we will have 2 eggs and 9 minus 2, 9 minus 2, or 7 drops. And then the question is, what is the tallest building that we can test with 2 eggs and 7 drops? We already know how to answer that question. We use our wonderful master formula. We compute the sum 7 choose 1 of 2 binomial coefficients. 7 choose 1 plus 7 choose 2. That will be what? That will be 7 plus 6 times 7 over 2. That will be 7 plus 3 times 7. That will be 7 plus 21 equals 28. So now we know that with 2 eggs and 7 drops we can test a 28-story buildings. We already know that this is a wonderful triangular number. So then the second story from which we will drop the first egg in the 3-egg case will be given by what? It will be 37 plus 28. It will be 7 and 8. 5, carry 1 over 6, plus 1, 66. So we will plus 1 will be 66. So here we will drop the first egg for the second time from the floor number 66. If the egg does not break there, we climb up to where? Well, we answer the question again by using 2 eggs, and this time 9 minus 3 equals 6 drops. So what is the tallest building that we can test with 2 eggs and 6 drops? Well, we know how to answer that question. Let me erase this right here. We will have here with binomial coefficient 6 choose 1 plus 6 choose 2. That will be 6 plus 5 times 6 over 2, which is 6 plus 5 times 3, it will be 6 plus 15, it will be 21. Again, we could have simply realized already that's the smaller, the previous smaller triangular number, but the sum of binomial coefficients wonderfully works out to 21. So the third floor from which we will throw our first egg will be what? Let's do it in our minds. 66 plus 21 will be 87, plus 1, 88. So we will throw the egg number 1 for the third time, if everything works out nicely, from the floor number 88. And it should be evident that by now this is where our scheme will terminate, because ideally the next throw will be way above the 100th floor. We only have 100 floors in the building, but if we want to know exactly the number of that floor, we will run the coefficients again, binomial coefficients. 5 choose 1 plus 5 choose 2, that will be 5, plus 4 times 5 over 2, that will be what? 5, plus 2 times 5 will be 10, 15. Again, we know that's the previous triangular number. This one was 21, this one will be 15. So let's do this. 88 plus 15 will be 103. 103 plus 1, 104. So in theory, if we were to run this test higher, then this will be floor 104, and so on. And the interesting question now, again, please keep good records of this information, it's not too complicated. We can turn the things around and inquire, okay, with 3 eggs and 9 drops, what is the tallest building that we can test with absolute certainty in order to determine the fate of the lowest bed floor in that building? Well, we simply plug in these numbers into our master formula and we compute the following sum. Let me erase this part of the proof. Hopefully you guys captured this in your notes already, and if not, then you can reproduce it, hopefully on demand. This is not too complicated, like so. So now, for the final stretch, for the final leg of this episode, let us do unwind this formula into what? 9 choose 1 plus 9 choose 2 plus 9 choose 3 comes out to what? 9 plus 8 times 9 over 2 plus 7 times 8 times 9 over 2 times 3, the 6 factorial. Wonderful. So here we get 9 plus 8 over 2 is 4. 4 times 9 is 36. That's 36. Plus 8 over 2 comes out to 4. 3, 9, 3 comes out to 3. 3 times 4 is 12. 12 times 7 is 84 plus 84. So what do we have now? Let's do this the old-fashioned way. 84, 36 will be, this will be 0, 120 plus 9, so this will be 129 is the number of floors that we can test with 3 eggs and 9 drops is the tallest building. And the scheme, you guys can build up that scheme. Over here we can see that from 88 to 104 we added 15 plus 1, so what will be the next number here? Well, the next triangle, smaller triangle number will be 10, so here it will be 104 plus 10, 114, so the next floor will be probably 115, and so on until we run up the height of the building to 129. And again, it should be evident that the numbers shown here in yellow are the numbers of the floors from which we drop the first egg, and if that egg does not break, we hop to the higher and higher floors over here, and if the first egg does break, then we go to the floor immediately above the highest good floor that we tested, and then we execute 2 egg testing scheme that we described below to to test all the floors below the usual suspect when the first egg broke. In general, this is how we go. Again, the same exercise can be repeated for 4, 5, 6, and 7 and more eggs, but interestingly enough, somewhat similar to how, for example, the Fibonacci numbers are computed. To compute the next Fibonacci number, we compute the previous one. So here, in order to come to a testing scheme with the larger number of eggs, we need to explicitly construct the testing schemes for all the previous smaller number of eggs. And for curious travelers, I would like to share you one more bit of information that has to do with what I refer to as restricted binary notation. This final segment of this episode is for true thinkers at heart, for those who are true mathematically oriented thinkers. Those who are not interested in this material can skip forward to the next challenge. But here I would like to share a little bit of an information that I was able to find when I was playing with all the zeros and ones. What happened here is when you execute all these computations and try to figure out, for example, how to test the given building, let's say 100 floors with 3, 4, 5, or 6 eggs or whatever, then what you may eventually notice is the following. If we switch again to the traditional binary notation, that traditional binary notation, we have no restriction on how many ones and zeros we use in order to record this or that number from in base 10. For example, here in this set of examples, I show how to record a given base 10 number shown on your left, to the left of the equal sign, and the corresponding binary representation. Maybe I can write down here is base 2, base 2, base 2, base 2, 2, 2, 2, and 2. So the interesting case over here, which I want to direct your attention to, is number 7. Look what happens between the binary representations of 6 and 7. Here we exhausted all the possibilities with 3 zeros and ones, and in order to add another bit of information to 6 and obtain the binary representation of the number 7, we slug in the third binary digit 1. All is good, everyone is happy, peace to the world, and joy all over the place. However, because we have in this case 2 eggs, I was thinking what will happen if we limit ourselves just to at most 2 binary digits 1 in the representation of the base 10 numbers. I refer to this as restricted binary notation precisely because in this restricted binary notation we still write the representation of this or that number in binary, but we restrict ourselves to precisely at most 2 ones. And this is where the difference comes in. When we go from 6 to 7, in the traditional binary notation, we have no problem slugging in an extra 1. But in the restricted binary notation, we cannot do that because we are limited to at most 2 ones. So what do? Well, instead of writing 1 over here, we shift the numbers. We pretend that we do not have anything to the right of this number, and we exhausted all the possibilities here. So we jump 1, 0, 0, and here I show the representation of the number 7 in restricted binary notation, designated with the prime sign over here, 2 prime. And this number looks as follows: 1, 0, 0, 0. Now the next number, the number 8 in base 10 representation, is business as usual. We keep rolling in the way in which we do things in the classical binary representation. We add 1 more, we add 1 more, we add 1 more. But here, because we reach the limit of number of ones in our representation, We cannot start slugging in ones over here. Remember, we are limited to at most 2 ones. So we do the next best thing, and we flip the 1 to the next bit position. We put zeros here and so on. But as a result of this experiment, what I notice is that all the triangular numbers, in this case, the numbers of interest to us, 10, 15, 21, 28, and so on, have precisely this pattern. On the leftmost side of their restricted binary representation, they have precisely 2 ones shown over here, and the number 6 also follows the same pattern, 1, 1, 0. Number 3, let me highlight it for you here, number 3 also follows the same pattern. The number 1 is the degenerate case, it's the trivial triangular number, so to speak. But as an alternative solution of the 2-egg and 100-story building, what we can do is the following. We can take the number of stories in this building, 100 for example, in its base 10, and convert it to RBN, to restricted binary notation. When such a number is converted, it becomes this. And what we do over here is we number the bit positions not from the traditional 0 on its rightmost bit, but starting from 1. In other words, we put the numbers to these bit positions like so: 1, 2, 3, 4, 5, and so on. That should be evident. And then counting right to left, starting from 1, we find the location of the leftmost one. And that leftmost one, the position of the leftmost one in the restricted binary representation of the given height of the building, precisely reveals the bracket number, or the number, the size of the first bracket, or the number of tests. Let's count over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The number of this bit position is 14. Consequently, the number of tests that is needed to determine with absolute certainty the fate of the lowest bed floor in the building with these 2 eggs is 14. And an interesting case over here for you guys to research is if there is a way to automate the translation of any number in base 10 to its restricted binary representation. And as I was playing with numbers, I only had the time to play with the case when the RBN is restricted to at most three ones. That corresponds to the case when that we considered just before in the previous segment for 3 eggs. And over there, I noticed the same pattern. For example, number 129 in base 10 was represented in restricted binary notation as 1, 1, 1, and 6, 0. So if we count and so on, so this, I'll put it down as 6, 0. So when we count the position of the leftmost one in the restricted binary representation of the number 129, that comes out precisely 9, the position number 9. So 9 is the number of smallest number of tests, or smallest number of drops, with which, with absolute certainty, it can be determined what is the lowest bed floor in the building that is 100 stories tall with 3 eggs. But determining the testing scheme over here may be a little bit involved, and this is for you guys to work out and enjoy. This is it for the theoretical part of solving the problem S2CS1, and we'll go to the presentation of the next challenge next. Our next challenge will be a problem in mathematics, S2M10. Don't forget that with the letter M we designate the problems in mathematics, with the letter CS we designate the problems in computer science, and with the letter P we designate the letters in the problems in physics. As such, in the mathematical problem S2M8, we're told that once upon a time there lived a farmer on a farm that is 1,000 miles away from the nearest market. The farmer once collected a harvest of 3,000 carrots, and he or she wants to sell these carrots at the market that is 1,000 miles away by delivering these carrots with the help of a horse. But the problem is that the horse eats precisely 1 carrot per each mile for each mile traveled. The question is, what is the largest number of carrots that the farmer can sell at the market and deliver these carrots from the farm that is precisely 1,000 miles away from this market? This problem can, of course, be solved in a number of different ways, but because right now we're studying the mechanics of the reverse order problem solving approach, we recommend that you try to find a way in which the reverse order problem solving approach provides at least some help and possibly helps you solve this problem. This is it for this episode. Thank you very much for your time. Thank you for watching. I'll see you in the next episode. The episode season 1, episode 8, in which I will discuss the solution of the problem S2M10.